Hey folks, welcome to this episode on predicting double displacement reactions. So we've seen this slide before where we have this first reaction occurring, but the second reaction not occurring. And we noted that for a reaction to occur, we have to have a change of state. And in this case, we do. We go from two aqueous compounds into an aqueous, and more importantly, a solid compound. And this reaction, for this not to happen, is that our two products are actually going to be aqueous. So the lead 2 chlorate and the potassium nitrate, both of them are aqueous in water, and so there won't be a change of state from your reactants to your products, and so we don't have a reaction. So our solubility rules and our solubility table that we've seen before will really help us figure out if this double displacement reaction will happen or not. So for a double displacement reaction to occur, either a precipitate is formed, a gas is produced, or water is created. So in the first case, what we look at is we have an aqueous compound plus an aqueous compound to produce an aqueous compound plus something that is solid. And this solid is called our precipitate, or PPT. In the case of a gas produced, now that could actually be happening directly, but more so it will be as a result of an aqueous compound being formed as a product and then being unstable. So what it actually does is it breaks down into a gas and something else. Or we can have a molecular compound. So again, in this case, if we're creating water, it's going to be as a liquid. So in all three cases, we're actually changing our states. We're going from an aqueous reactant to some kind of solid, gas, or liquid product. If there is no change in the state from the left side to the right side, the reactant to the product side, no reaction will occur. So if they remain aqueous, there's no reaction. And again, we look to our solubility rules to figure these things out. So here's a step-by-step as to how we can figure out what the products of a double displacement reaction would be. Now remember that in a double displacement we have two compounds reacting. In a single displacement we have an element plus a compound. So in this case I have my iron 3 chloride and my sodium hydroxide, both in their aqueous states. And the first thing I want to do is identify my cations that are going to switch. So here I have my iron and I have my sodium. Now, some people like to switch the anions, some people like to switch the cations. I just prefer switching the cations, so that's what I'm going to do here. So my iron is currently with the chlorine, or the chloride ion, and my sodium is with my hydroxide ion. And so what's going to happen is that these two metals are going to switch places. So my next step is just rearranging the cations. You notice that I've kept my chlorine in the same place, my Cl, and my OH in the same place, and I've switched the cations, in this case the metals, in the compounds. Now notice how I haven't created a formula yet. I just rearranged them, I put them beside each other. I haven't yet done the formula because I first need the charges. So my charge for sodium on the periodic table is 1 plus, chlorine is 1 minus. Fe comes from here. Well, here I have my 3. I'm going to put that on top of the Fe. The kind of subscript beside Fe, which is 1, goes over here. The real charge of chlorine is minus 1, so the charge of Fe is 3 plus. For memorization, I know that hydroxide is 1 minus. So what I do here is I use my cross-down method to figure this out, and I get NaCl plus FeOH3. Now, to determine if this reaction has actually happened, if these products have actually been formed, I have to look at my solubility table and figure out what states they exist in. So here on the top here, I have a little bit of a little cutout of a solubility table. My Na with the Cl is going to be S, so that's soluble. That means it's going to be aqueous. And my Fe3 plus with the OH says I, and that means it's insoluble, and something that is insoluble has a solid state. So here I have aqueous and solid, so absolutely this reaction has occurred. Last thing I need to do is balance. So let's take a look at this reaction where we have lead 2 nitrate and potassium iodide. We want to try to figure out if this double displacement reaction has occurred. So the first thing we want to do is we want to identify what our cations are. Here I have my Pb and I have my K. So those are going to switch places. I'm going to put my K here with my NO3. I'm just kind of putting them beside each other. There's no formula formation going on yet. And I have my Pb and I have my I. So my K and my Pb have switched places. I left my nitrate and my I together. Now remember that these subscripts do not follow necessarily onto the other side. You have to create the new formulas using the cross-down method. So for that we need the charges. For potassium it's 1 plus, for nitrate it's 1 minus. For Pb Well, again, I get this charge from here. If I do my up cross over there, and this goes here, this becomes 2 plus, and that's 1 minus. I compare the charge of the nonmetal, which is minus 1, so that means that the charge of Pb is 2 plus, so I get 2 plus. And for my periodic table, this is 1 minus. So I cross-cross, and I cross-cross, and let's see what I get here. So I will get KNO3, make that a little bit better, KNO3 plus PbI2. Okay, now what we need to do is we have to figure out if this reaction has occurred, and the way that we do that is by looking at the states. So in my solubility table here, my K and my NO3 in this case is S soluble, so that means the state beside KNO3 is going to be aqueous. And looking at my Pb and my I, so here Pb and I will be I, so that's insoluble. That means that it exists as a solid. So yes, this reaction has occurred. The last thing that we need to do is balance. And so I'm just going to rewrite my reactants here, my PbNO3 2 aqueous plus Ki aqueous gives me this. So to balance, I have 2 NO3 is on this side, so I'm just going to put a coefficient of 2 here. That means I have 2 Ks. I now have 2 I's over here, 2 I's over here, and I'm balanced. So let's look at this one over here, magnesium nitrate and potassium chlorate. So this one's one step more challenging because we have to create our initial products, our initial reactants, excuse me. So Mg, let's just do our formulas. We have Mg and we have NO3. This is 2 plus, this is 1 minus. So when we do our down cross, we'll create that formula. And potassium chlorate, potassium is K, chlorate is ClO3. This is 1 plus and this is 1 minus, we cross cross. So let's just rewrite these formulas over here. We have Mg, and that's going to be bracket NO3 2 plus KClO3. Now we have to figure out what the states are. So again, we have our little solubility table here. My Mg and my NO3, it's S soluble, so that means it's going to be aqueous. And my KClO3, this is soluble, so that means it is also going to be aqueous. Alrighty. So again, in this case, I want to identify what two things are going to switch. In this case, my Mg and my K are going to switch places. So that means I'm just gonna rewrite them over here. So I'm going to have my K and NO3. Again, I'm not creating formulas, I'm just rearranging them. And I have my Mg and I have my ClO3. Now to create the formulas, I need the charges. This is going to be 1 plus, this is going to be 1 minus, this is going to be 2 plus, and this is going to be 1 minus. So if I cross-cross and I cross-cross, I get my formulas. So my formula is going to be KNO3 plus Mg bracket ClO3 2. Alright, now we have to figure out what the states are. So again, I go back to my solubility table and I have my K is now with my NO3, that's S. So that means that it's going to have a state of aqueous because it's soluble. And my Mg with my ClO3 is going to be S. So that means that this is also going to be aqueous. Now, we have an aqueous and an aqueous reactant group. So we have both reactants aqueous, and both of our products are also aqueous. Now what this means is that there has been no reaction. There's no change in state, no gas produced, no liquid or no solid precipitate produced. So the way that we rewrite this is that we'd say Mg NO3 bracket 2 aqueous plus KClO3 again aqueous gives me NR, which stands for no reaction. So here are some practice problems for you. Use your activity series and try to produce the products here. So again, identify which cations are going to switch, rearrange them, create the correct formulas, look at your solubility table to figure out what the states are, and determine if there is a reaction that happens. If there's no reaction, you don't have to actually write the products out. As you get better with this, you'll be able to figure that out before actually going through all the steps. but you can simply just write NR, which shows that there is no reaction. So go ahead, pause the video now, and we'll come back in a few moments with your answers. So welcome back. Here are the answers. The first two reactions do occur. So you will have in the first one we'll have a solid precipitate of calcium hydroxide produced. In this case, you'll have lead to chloride produced, and these are your balanced formulas. The third one, there's no reaction. So these are what the products would have been. Again, products in quotation marks. But you can see that they're both going to be soluble. Okay. So because both of them are soluble, we can just write in this equation that there's not going to be a reaction. Once again, we have a reaction occurring. We produce this silver sulfate precipitate. And the last one, again, no reaction because this acetate and sulfate is going to be soluble in water. So you have no change in state, so we have no reaction. All right, folks, thanks very much for watching. See you next time.